Hi, today we'll be discussing innovations for Java running in containers. My name is Toby, and I'm joined here with Marius Purvu and Hung Shao. About a decade or so ago, the common form of deployment were large applications that did everything. These were termed monolithic applications. In this world, applications had long deployment windows. They ran for long periods of time, weeks, sometimes even months. They were typically deployed in large on-premise server farms. Typically, you owned all the hardware, and the hardware was mostly uniform. Since you owned all the hardware, typically your resources were static. It's not easy to dynamically increase capacity in this kind of paradigm. One has to purchase more hardware. So people normally end up getting more resources than they need in case of a spike in demand, as acquiring new hardware takes time and you don't want to have outages. So over-provisioning was the norm. Nowadays, there's been a shift in how people deploy and architect their applications. Instead of one large monolithic application that does everything, people modularize their apps into many smaller services. Deployments are frequent and may happen even multiple times a day. As a result, people often employ CI/CD pipelines to streamline delivery. Typically, applications are deployed on public clouds, and since it's running on the cloud, it's easier to scale. There's not a finite limit on resources in the cloud. So you can provision just the right amount. And as the demand changes, you can scale up or scale down to that demand. With the shift to the cloud, there's also a shift in challenges. So we'll look at some of those now. With microservices, you have many dependencies to manage. There are many different environments in which an application may be deployed to, and resources may not be uniform in the cloud. Platform characteristics may vary between different nodes. One node may have more memory than another, or may be using a different version of the CPU than another. Due to cloud economics, where pricing is often based on memory and time usage, over-provisioning is not a good option in dealing with changes in demand, which means that you want to scale up or down. There is a direct correlation between scaling time and the latency that end users may experience when the demand suddenly increases. Containers provide some solutions to the challenges in the cloud deployments, and we'll look at some of the benefits of using containers. With tools like Docker, it lets developers modularize and package their solutions into immutable entities. This means they get the same configuration in development, testing, and production. This solves the problem of dealing with multiple dependencies and makes it easier to deploy in different environments, and thus reduces the risk when deploying. With container solutions, it's easier to deploy to different clouds and platforms, since all your dependencies are contained within the image. Containers are an effective means to address some of the challenges in the cloud, but they do not address all the issues that developers may have in cloud environments, such as cold starts, minimizing footprint, something that people running JVM-based applications are very familiar with. Startup time is important because with microservice-based solutions, typically there are many instances and they typically aren't run for very long. This differs from the monolith systems where startup time can be negligible since the applications run for long periods of time. With function as a service and serverless solutions, startup time is very important as the startup time is a noticeable portion of the application runtime. Also, with dynamic scaling policies, startup time directly correlates with the response time as one needs to spin up new instances as demand increases. Given that pricing for cloud environments often depend on memory usage, it benefits application developers to minimize the size of their apps. The ability to tune the JVM is very important in these cases. Containers do not solve all the challenges on their own, but they do offer JVM providers an avenue to provide solutions to address some of the things that containers can't on their own. Containers offer a modularized entity which people can package their applications as well as JVM enhancements that ensure optimal performance in cloud environments. Next, Marius will describe what some of these enhancements are and how users can leverage them in container-based solutions.
In the following few slides, we are going to detail a few OpenJ9 features that are geared towards improving performance in cloud environments, and we are going to interleave those slides with short demos that showcase the performance benefits of those features. But before anything else, let's describe our experimental testbed. As application, we'll use the well-known pet cleaning benchmark which runs on top of the Spring Boot framework. All the experiments will be performed on an Intel Skylake machine with Ubuntu, and we are going to look at startup time, footprint, and container image size. The correct way of measuring startup time is to memorize the timestamp just before launching the JVM, obtain the timestamp of the line that says the application is ready, and subtract the two. However, for simplicity, in these demos we are just going to record the startup time reported by the application itself, which is a good approximation of the real startup time. Obviously, this measure does not include the delay to start the container, but that is a fixed quantity that does not depend on the JVM. If you are curious, on my machine it takes about 250 milliseconds to start up a container. For footprint, we report the resident set size of the application obtained with the Linux PS command. For container image sizes, we report the size on disk from the Docker images command. Speaking of images, I put on the slide the tags of the Java GRE layers on top of which we are building our pet cleaning container images. So these are pulled from Docker Hub. For OpenJ9, we are going to use two different images because release 0.23 contains some additional improvements over 0.20 that we'd like to highlight here. So let's switch to the demo. In the bottom left corner, you can see the container images that we are going to try. For our experiments, the baseline is a pet cleaning container based on the hotspot Java 11. So let's have a quick run. So I'm going to say docker run -it, and it's always a good idea to specify limits for your container. So I'm going to limit the container to just 4 CPUs, and I'm going to limit it to half a gigabyte of memory. And then I need to specify the image name, which is pet clinic, and the correct tag is this one from here, which I highlighted. So let's fire it up. Have to wait a few seconds until the value appears, and of course there could be some small variation from run to run, so we shouldn't read too much into that. So in this case, as you can see, the JVM with hotspot started up in 5.4 seconds, and I'm going to record this value in my Excel spreadsheet. While the application is started, let's have a look at the footprint that it takes. So this is obtained, as I mentioned before, with the PS command. So looking here in the bottom right corner, we see that hotspot takes about 278 megabyte of memory. So let's put this in our spreadsheet. While for the image size of the hotspot container, on disk, we can see from here that it takes 295 megabyte. So let's add it to our spreadsheet. Now we are ready and we can close this. So now let's see the performance of Pet Clinic with OpenJ9. We'll start with the older release 0.20. So I'm going to use the exact same command, the exact same limits, but the tag is going to change. Instead of hotspot, I'm going to use OpenJ9 with Java 11 and release 0.20. It's probably going to take slightly more than hotspot because 0.20 does not have any changes related to improving startup time in containers. So indeed it takes 6.5 seconds in this case. I'm going to record this. But we expect the resident set size, so the footprint taken by OpenJ9, to be much smaller, and indeed it is 189 megabyte. So in fact, one of OpenJ9 signatures is its small footprint, fact recognized by many independent tests. While for image, we read it here from our table, it's 269 megabytes. So let me put it here. So this is slightly better than hotspot, so 269 compared to 295. Class verification adds a bit of overhead during startup when many classes are loaded, and therefore we took some steps to improve it. We introduced a feature called Class Relationship Verifier that omits class loads that would have occurred during verification, and instead it creates a record of them, a record which is then verified later on at runtime. With this feature, some of the class loads may never happen, and this can improve startup time slightly. This feature is not enabled by default, but it can be turned on with the option that I specify here, XX: plus class relationship verifier. So let's go back to the demo and see how this option behaves. I'm going to use the same option as before, the same command as before, but I'm going to add an option to the JVM through the environment variable, which I'm going to copy because I don't want to do any typo. So this is the option. So let's fire this up and see how it behaves. The expectation is that startup time is going to improve slightly, and indeed in this case it took 6.1 seconds with the class relationship verifier. So let me record this time, and let's also look at the footprint taken by this configuration. In this case it's 179. It looks like a small improvement over the previous value, but you shouldn't read too much into it because there is fluctuation run to run. In fact, there isn't, we don't expect any footprint improvement from this option. And the image size, of course, is going to be the same because I am running the exact same image. So I'm going to record that value as well. Now let's go back to our presentation. So one of the main ways of improving startup time with OpenJ9 is the shared class cache technology, which in a nutshell is a memory map file used to cache mainly three things: the read-only part of Java classes, the AOT compile code, and interpreter profiling information. Since classes are loaded from memory instead of from the disk, and because they are already pre-processed, class loading is much faster with the shared class cache, and this improves startup time. Another key technology that improves startup is dynamic AOT. We call it dynamic because methods are compiled to a relocatable format at runtime and stored into the shared class cache. Any subsequent JVM instance can reuse these methods after a cheap relocation process, which is about 100 times faster than a normal JIT compilation. So with AOT, the JVM is able to transition faster from interpreter to machine code and to improve startup time as a result. The downside is that the AOT code is slightly less optimized because it is more generic, as it needs to fit many JVMs. But we can mitigate this issue by generating AOT only during startup phase of an application and by recompiling the AOT method bodies with the regular JIT compiler. However, when we use the shared class cache in containers, we have a problem. The shared class cache that is being created and populated by a run disappears once the container is terminated, so we never get to take advantage of the cache data unless we ensure some persistence across runs. Persistence is typically done with volumes, but in order to make the technology more user-friendly, we decided to embed the shared class cache into the container image. Basically, the cache is populated when the OpenJ9 container image is created by starting and stopping Tomcat. Now, because the OpenJ9 image may be used by many applications, we do not cache classes and AOT methods from the Tomcat application itself, but restrict the caching to classes and methods loaded by the Bootstrap class loader. This provides a limited amount of caching, but should be generic enough such that any Java application can benefit from it. We call this cache OpenJ9 System SEC, and starting with OpenJ9 release 0.23, you can take advantage of it. So let's see how this behaves. I'm going back to the demo. So we are going to use a similar command as before, but I'm going to change the tag to 0.23 and I'm going to skip this class relationship verifier option. So the expectation is that there will be a significant improvement in startup time. And indeed, as you can see here, we are now catching up to Hotspot. So the startup time is exactly the same as that of Hotspot. Looking into the footprint, it turns out that the footprint is 181 megabyte. It's actually about the same as before. And if we are looking at the image size, release 023, which is this here, takes 302 megabyte. So this is clearly larger because it embeds, the image includes an embedded share class cache. So it is expected to be larger. So, but it's just slightly larger than the image with a hotspot. Okay, so now I can kill this and let's go back to the presentation. As you can imagine, we can do better if we allow caching for classes and methods belonging to Spring Boot and pet cleaning app. The methodology is similar to creating an OpenJ9 base image, so we are going to populate this cache during container image creation time, but this time we start and stop pet cleaning application itself. Now let's remember that the OpenJ9 base image already has an embedded cache. So we could use the same cache to store pet cleaning classes too. However, if we did that, due to the copy on write mechanism, the moment we try to write into cache, a copy of the entire SEC is going to be created for the new layer, increasing total image size. The problem is amplified by the fact that we don't know how big to make the share class cache in the base image. Since user could be using the base image for large applications as well, we should be quite generous with its size. So let's say 100 megabytes. But that means that we are going to replicate 100 megabytes for every new layer that attempts to add something to the cache. To avoid this problem, OpenJ9 improved the share class cache technology to work in a layered fashion as well. So basically, at each Docker layer, we create a corresponding share class cache layer that is sized just right for the classes and AOT methods that it needs to hold. Using this multi-layer share class cache approach, we created another pet cleaning image which embeds not just the Bootstrap classes and methods, but also classes and methods from the application itself. So let's see how this performs in terms of startup time. I'm going to switch back to the demo. So I'm going to use the same command as before, but of course the tag has to change to include the multi-layer share class cache. And the expectation is that the startup is going to be faster, and indeed it is way faster. So startup time is just 2.9 seconds, a clear improvement versus the previous versions. Let's look at the footprint. I'm using the same ps command, and the footprint is 183, just slightly larger than the previous value. In terms of image size, of course, we expect an increase. So the image size for this container, which has the multi-level share class cache, is 343 megabytes. So I'm going to record it here. We should expect an increase in image size because the cache that is embedded into the image is definitely larger in this case. Now let's go back to our presentation. Finally, let's look at a graph I generated repeating the above experiments 20 times and plotting the average values. All the configurations I talked about are included in this graph, while the last bar represents the single layer share class cache configuration, which I included as a reference. For these experiments, I used a more rigorous methodology for measuring startup time. The first grouping of bars look at the startup time. The first bar represents the normalized startup time of hotspot, which is our baseline. The second bar, in orange, represents OpenJ9 release 020, which does not have the startup time features described in this presentation. As you can see, there is a 17% slowdown compared to hotspot. If we add the class relationship verifier option, we can gain about 7 percentage points. The bar in yellow is OpenJ9 release 023 with the embedded system share class cache, and at this point OpenJ9 becomes slightly better than hotspot in terms of startup time, but not by much. The big improvements come once we move to release 0.23 with multiple level share class cache, and this configuration allows caching of classes and methods belonging to Spring Boot and pet cleaning. If we add the class relationship verifier on top on the previous configuration, this is the bar in green, then we can improve startup time by another 2 percentage points. So all in all, the best OpenJ9 configuration is almost twice as good as Hotspot in terms of startup time. In terms of footprint, the first thing that jumps at you is that all of the OpenJ9 configurations clearly outperform Hotspot by a large margin. So there is a small footprint increase once you move from release 0.20 to release 0.23, and this is due to the embedded share class cache. However, we consider that footprint increase to be totally worth it, considering the big gains in terms of startup time. In terms of image size, which is the last grouping, OpenJ9 has a small advantage with release 0.20 over Hotspot, and once we move to release 0.23, the image size increases due to the embedded share class cache. Moreover, if we allow caching of classes and the methods belonging to the application, the size of the share class cache is going to increase, which in turn is going to determine an increase for the image size. Again, we think that the huge improvements in startup time make this increase in image size totally acceptable. The last bar shows what would have happened if we cached app classes but used a single layer share class cache. Due to the copy on write mechanism, we will have had an increase in image size with no tangible benefit for startup time or footprint. All in all, I hope that this demo convinced you about the features OpenJ9 has in arsenal to improve startup time of Java applications run in container without unduly increasing image size. JVMs can experience an out-of-memory event when they need to allocate an object. There is not enough free space in the heap, and the heap cannot be expanded anymore. This is what I would call the traditional out-of-memory issue. However, to function, JVMs need not only the Java heap, but a slew of other internal data structures, and these fall into the so-called native memory category. If the JVM experiences a native out-of-memory issue, it may be forced to shut down, or at the very least to forgo some of its functionality. The JIT compiler is a big consumer of native memory, and this is no surprise given its complexity. In OpenJ9 parlance, the memory needed by the JIT compiler is called scratch memory. Scratch memory is allocated on demand in 16 megabyte increments and up to a limit of 256 megabyte per compilation thread. The good news is that scratch memory is fully released to the operating system at the end of the compilation. The bad news is that the compilation activity is conducive to transient memory usage spikes, which may generate a native out-of-memory event. The graph at top right, which plots the OpenJ9 memory usage during a run of the pet cleaning application, clearly shows these footprint spikes, which are due to the JIT compilation. In contrast, Hotspot JVM, shown in the graph bottom right, does not have footprint spikes, but its footprint envelope for steady state is higher than that of OpenJ9. We assume that this behavior is because Hotspot does not fully release to the operating system the memory used during the compilation. It should be mentioned that the memory allocated with malloc and subsequently freed, it is still kept in malloc's internal buffers for future allocations, and therefore it's still part of the resident set size. When running applications in containers, you typically set memory limits for those containers. One reason could be to avoid faulty JVMs that could hog a humongous amount of memory. If the JVM attempts to allocate more than its limit, then the container runtime is going to terminate the container. Now, suppose your application mysteriously dies. How can you tell that it was the victim of an out-of-memory event? Well, you could use the docker logs command, like I've done here, but maybe more relevant is to use the docker inspect command. If your application experienced an out-of-memory event, you would see an out-of-memory killed set to true as shown here in orange. Having seen that the JIT compiler can trigger a native out-of-memory event, now let's turn our attention to how we can avoid such a scenario. OpenJ9 makes a best effort to avoid native out-of-memory events due to scratch memory consumption, and to do so it constantly monitors memory availability, taking into consideration the container memory limit, the amount of memory used by the JVM, and the amount of free memory on the machine. When available memory runs low, the JIT compiler may fail some compilations, or if the memory situation is dire, it could also turn off compilation threads. However, the mechanism is not perfect because memory availability could change soon after the readout has been performed. So, despite our best efforts, spurious out-of-memory events could still happen. So let's look at the graphs on the right. The top graph shows the footprint of OpenJ9 when load is applied to the pet cleaning application. On the x-axis we have the time, and on the y-axis we have the resident set size, that is the footprint. There are two lines corresponding to two different container limits, 1024 MB and 512 MB respectively. As shown, when the container memory limit is reduced to 512 MB, OpenJ9 will reduce its memory consumption, trying to stay within the given limit. As you can easily see, the footprint spikes are much smaller when the limit is just 512 MB. However, this is not always successful, and in these experiments 2 out of 10 attempts ended being killed due to the native out-of-memory. If you are wondering about hotspot, well, all attempts were killed by out-of-memory. In essence, hotspot cannot run with just 512 MB of memory. The graph at the bottom plots the throughput of the pet cleaning application for the same two container limits. The throughput of the 512 MB config, which is the line in orange, is much lower than the throughput for the 1024 MB. The explanation is that OpenJ9 downgrades compilations and shuts down compilation threads trying to stay within the given limit. So OpenJ9 prefers to operate at a lower capacity rather than crashing the application. In the previous slide, we've seen that despite our best efforts, if not enough memory is available, OpenJ9 can still experience an out-of-memory event. In order to make that event less likely, we have an add-on solution, and that is the Extune Virtualized mode. Extune Virtualized is an option recommended for users who run in resource-constrained environments that are typically found in the cloud. Under the hood, the JIT compiler will reduce somewhat the aggressiveness of certain optimizations, which results in less CPU and memory consumed by the JIT compilation threads. More recently, under Extune Virtualized, we've also reduced the limit of scratch memory to just 16 MB. Remember that scratch memory is the native memory used by compilation threads. As a result of this reduction, some of the compilations are downgraded to a lower optimization level, and the peak throughput may be negatively impacted. So let's see how this option performs. So let's turn our attention to the graph at the top, which shows the footprint values when load is applied to the pet cleaning application. Both configurations have a 512 MB of memory, but the line in orange uses Extune Virtualized. As can be seen, the memory usage for this configuration is much lower, and the peak memory consumption is well below the 512 MB limit. We have not seen any out-of-memory event in more than 20 runs, while for the line in blue, as I mentioned previously, we've seen 2 out of 10 out-of-memory induced crashes. What's surprising is that the Extune Virtualized config also delivers better throughput, as shown in the graph at the bottom. As you can see, the line in orange is well above the line in blue. The explanation is that under Extune Virtualized, the JIT compiler performs fewer optimizations, while for the line in blue, the JIT compiler is forced to fail compilations and to shut down compilation threads. The takeaway is that if your application is running close to the memory limit, Extune Virtualized could be a good solution not only to avoid out of memory, but also to achieve good enough levels of throughput.
OpenJ9 has AOT code that speeds up the application startup, which is stored inside the shared class cache. The code run builds and populates the shared class cache. You get startup benefits from subsequent warm runs that load cache the data. As we seen in the previous demo, We got startup performance improvement after prebuilding an embedded shared class cache into the Docker image. So when deploying your application on the cloud, you may want to do the same thing to embed a shared class cache in your Docker image. In this way, your application will have better out-of-box performance due to the cached data that comes with the image. However, the embedded shared class cache needs to address one issue: the portability of AOT code. The build time environment may not be the same as the runtime environment. There are many factors that could invalidate the AOT code, like different CPU features, different heap sizes, different memory barriers, etc. OpenGNI introduced a new command line option to generate portable AOT. This option is turned on by default inside container. One nice feature about OpenGNI is that it is container aware. So OpenGNI automatically generates portable AOT code for you when running inside container without the need to explicitly turn on this option. The real value of portable AOT is that it ensures that AOT code is used in more cases, since the performance difference between using AOT code versus not using it could be as much as 60% in our experience.
To summarize, the ability to configure JVMs is an important tool in getting the best performance for your application when running on the cloud. Startup time and low memory footprint are important characteristics for efficient cloud deployments. OpenJ9 is optimized to have low memory footprints. It also provides tuning knobs that enable faster startup. OpenJ9 is also container aware and has options to enable high performance in resource-constrained container environments. This concludes our presentation on innovations for Java running in containers.